Hey, hello, hi. This is a video on. I want to provide a little bit value on two pointer technique, um, two pointer technique, and how I kind of see things in my mental model for this two pointer technique. So usually, in the case when you have a when they have a target value, when you find all the pairs or the number of pairs that exist in this particular array or bound um, that are smaller than this target value or bigger than target value, right? Um, Usually, you can exploit the fact that the array is sorted, or the array this exploit the sorted array property. So when the array is sorted, and when the array is sorted, and when you make the comparison between the summation of lower bound and upper bound values with t, so comparison of the summation of with sigma with t, you can tell us when you do this comparison, it will tell us something about all the sigmas that can be made with LB, or in terms of, okay, I'm going to simplify this, but I'm just going to say all the pairs of LB, which and all the pairs of upper bound. Um, so so okay, I'm not for sure if I explained that well, but okay. So imagine the sigma. If imagine a grid over here, you have this upper bound, and imagine all the sigmas that a lower bound can form, and these are all the sigmas that upper bound can form. Um, and if the target value can lie on the left side or the right side, right? And this is the same thing. These are the same values. This is the same sigma if you realize. So yeah, target value could be on the left side or the right side. Now, now when the target value is on the right hand side, right? As you can see, it could fall anywhere in this particular region, right? In this particular row, it could fall. This t value could be anywhere in this particular. So we cannot make generalization on the all the pairs of the upper bound. However, if you follow this line, it's the same thing over here. We can make generalization on all the values of the lower bound, which is, we can say, oh, t exists here, so all this value, right? All this value must be smaller. All this value must be smaller than this particular t value, right? On the other hand, when the t value lies on the left hand side, um, we can say, hey, okay, we can, because it can lie anywhere in this particular row, we cannot make any generalization about the lower bound values pairs, but we can make, if you follow the line, we can make generalization on all the upper bound values, which is, hey, you know, all the sigmas that all the pairs of this upper bound value will be bigger than t, right? So a more compressed, I guess, like there's a more compressed a compressed diagram or mental model. You can compress this mental model down into even simpler form, which is like you could draw this like this right angle triangle, which represents the summation, right? Which represents each line, I guess, like, which represent a summation value. And in a sorted array, it's a right angle triangle because it's a sorted array, right? And you have the sigma in the middle, and these two things are equal because they represent the pairs summation. This triangle, each triangle are different, even though they look the same because they represent the pairs of upper bound and lower bound. And the t value could lie somewhere over here on the left right hand side or left hand side. And if t value lies on the right hand side, you can kind of follow this line and say, hey, I can make generalization on all the lower bound values. Or when t is on the right hand side, the left hand side, you can kind of say, hey, I can make all generalization on all these values. Um, and once you have that in mind, it's literally just it just becomes a counting problem. But that's it. Thanks.